Plane pi has Cartesian equation as given here. We want to determine a vector that's normal to the plane pi. So we could rearrange that into 2x plus y, take away z, is equal to -4. And then that's in the usual Cartesian form for a plane. And from that we can read off that the normal is 2, 1, -1. We're now given a line just here. Determine the point of intersection between the line and the plane. So reading off from the line, we can see that x is going to be 2 plus lambda, y is going to be 2 lambda, and z is going to be 3 take away lambda. And then we can just substitute these into the plane. So we get twice 2 plus lambda plus 2 lambda, take away 3 take away lambda, is equal to -4. You could solve that just on the CAS now, but it's pretty easy anyway. 4 plus 2 lambda plus 2 lambda, take away 3 plus lambda is -4. So how many lambdas do I have here? I've got 5 lambdas, and I've got +1. So 5 lambda equals -5. Lambda is -1. And so the point of intersection, substituting back over here, we're going to have 2 take away 1 is 1. 2 times -1 is -2. And 3 take away -1 is 4. So what's next on this question? Plane pi contains the line L. Plane pi 2 contains the line L and is perpendicular to plane pi 1. Determine the vector equation for plane pi 2. So if this is the plane pi 2, we know the line L1 is in it. That gives us a point because that means 2, 0, 3 is on the plane. So 2, 0, 3 is on the plane. And it also gives us a direction because the direction must be parallel to the plane. So that's 1, 2, -1. Now, if it's perpendicular to the other plane, that means the normal to the original plane is also parallel to this plane. And that was 2, 1, -1. So if we want the normal to this plane, we can find that using a cross product. So we've got I, J, K. I've got 1, 2, -1, and 2, 1, -1. So cover up I on the top, and we've got -2, take away -1, so -2 add 1 to -1. Covering up the J, we've got -1, take away -2, -1 add 2 is 1. Of course, this one always gets the sign changed. And then here we've got 1, take away 4, -3. Now, since they're all negative, I might just use the positive. So we've got R dot N is A dot N. So we've got R dot 113 is equal to A, which is a point on the plane. The 2, 0, 3 would do nicely there. Dot 113, which gives us R dot 113 is equal to 2 plus 9, which is 11. sphere S has an equation as given here. I'm just going to rewrite that using column vectors. And we want to know whether the line L is a tangent to the sphere and justify our answer. Well, we could do that with the number of points of intersection. A line can either not intersect the sphere at all, intersect once, in which case it must be a tangent, or twice. So let's go back and get the line. It was 203. 203 plus lambda 1, 2, negative 1. And so we can substitute that into here. So what have we got? 2 plus lambda, 2 lambda, 3 take away lambda, take away 3, 1, 4 is equal to root 35. So 2 take away 3, negative 1. So we've got negative 1 plus lambda, 2 lambda take 1, and negative 1 take lambda. That's equal to root 35. And that would give us negative 1 plus lambda squared plus 2 lambda take 1 squared plus negative 1 take lambda squared is equal to 35. So remember, the modulus would have a square root, so I just squared both sides. Now this is only 3 marks, so I'm going to solve this on the CAS. So I've typed all of that into my ClassPad, and if I execute, I can see there's 2 solutions. So we get lambda is equal to negative 2 or 2 2/3. So it's not a tangent.